Do a little check here to make sure we're live. I guess you're up, so it should.
Live. It says live. Ooh.
And there we are.
Hello.
All right. Hi, everybody. I'm Ryan, as you guys have known from our videos, and this is Phil.
Howdy.
And we're going to go through some of your questions that you guys have submitted. The first one we want to talk about is the messages about the uploading problems. We know that lots of you are having trouble with uploading your assignments and uploading the knowledge checks and stuff like that. edX is definitely working on it. They are aware of it, and we hope to have a solution in the next couple of days, if not today. They're working hard on it. Continue to email gfa@edx.org with as much information as you possibly can. Screenshots, description of the problem, that sort of thing. The louder we are, the faster edX is going to help solve our problem, the more pressure they'll feel. So we're frustrated as much as you are, and we want to see this work and be a great experience for you guys. Do note that the knowledge checks are not graded assignments, so they won't count against your grade. You'll get a score, but they won't count against you if it doesn't work out in the meantime. The first graded assignment is coming up. It's going to open on August 26th. That's the project challenge at the end of week 1. So do watch out for that. It is an ORA, but we're going to be grading it. So it might not have the same kind of issues, but we're hoping that all these problems are fixed before then. If they're not, we will work with due dates and all kinds of stuff to make sure that everything is going smoothly. So nobody will get held back because of technical issues on our side, okay? So thank you all for bringing that to our attention. If you find anything else that's wrong in the class, please let us know and make sure and give us lots of information so that we can try and solve the problems as we go. Again, this is the first run of the class, so we're all going to be finding lots of bugs, and it'll be really helpful for you to send that information to us.
So the next question is also a course-related question, and it is, do we have to ID verify for the course if we just want to learn from the course material? And the answer to that is not at all. The entire course is free and open to anyone that has access to a computer and the internet. The ID verification is in no way required. And that leads into the third question, which is, what are the benefits of getting ID verified and paying the $49 fee? And there are 3 benefits, really. The first is you get rich, individualized feedback on your graded assignments. And then you also can get a certificate of completion showing that you completed this course. And this gives you the option to obtain ASU transfer credit for ASU's CSC 110 course at a cost of $200 a credit, which is a substantial reduction from the normal fee. So it's not required, but it does have benefits.
Mm-hmm. Yeah, and the idea here is we're trying to make this super low risk for everybody that's here. If you want to try it out and get some feedback from us, it's a very low investment. And if you don't like it, it's not for you, that's totally cool. And we hope you find your passions here. But if you do and you want to keep pursuing it, it's a great opportunity, and we hope you guys, you all enjoy this as much as we do, because we're having a blast. I think this is turning out awesome, despite some of the technical issues that we're having.
Cool. So on to the more course topic specific questions here. We had several questions asking about which is the easiest programming language to learn. If you ask that question in some crowded rooms, you might start a fight. I don't think Ryan and I are going to fight over this. We obviously have some opinions, and they're built into this course. We believe, while I'm not going to argue that Python is the easiest programming language to learn, it's definitely going to be on my list of the top few. And so that's why we are starting this course out with the Python programming language. It is one of the easier languages to learn, and the reasons behind that are it tends to have a more simplified syntax. It doesn't require you to learn and be aware of a bunch of very strict minutia about where you put parens and curly braces and semicolons like some other languages. And it also allows you to do quite a bit with relatively little code. So some programming languages will require you to write 10 or 12 lines of code just to get some text to appear on the screen. In Python, you can do those kinds of things in one line of code. So
there are some simpler languages that we did look at using. There are some block-based languages like Scratch or Blockly, those sorts of things that are highly visual, and they're usually tuned for a much younger audience. We're talking like junior high, grade school type of classes. And those are options if you want to get the basics down. But we wanted to teach you guys some of the skills and concepts of programming, including all the typing and stuff like that, while giving you skills that are applicable to a lot of job domains. So Python is used a lot in the industry, as is Java, which is what we're going to be teaching in the second half of the class.
Right. And that leads into our next question, which is, why are there so many different kinds of programming languages? And again, we're probably not going to be able to do justice to an answer here. We would need to bring in a linguist if we were going to do a really good job of answering this. But part of the answer is similar to asking and answering the question of why are there so many human languages like English and Spanish and German and Japanese and Arabic. And the answer is because there are so many human cultures. Wherever you have a group of people that get together kind of geographically and engage in some behaviors to work together, there's going to be a set of shared norms and beliefs and culture, and a language springs up around that. And the same thing is true for technical cultures. So many of the programming languages that we have today came about by a group of people engaged in a particular technical endeavor. For example, C was invented at Bell Laboratories back in the 1960s by some people who were trying to solve a particular problem there, and existing tools weren't meeting their needs, and they designed a programming language to meet their needs. And so this has happened several times in a lot of different places, and there are a lot of different programming languages out there because of that. And they all tend to have their strengths and their weaknesses.
Mm-hmm. Yeah, so for instance, I come from a hardware background. I developed a lot of embedded systems programs. I built robots and stuff like that. And in that environment, C and C++ are super common. These are languages that work very closely with the machine itself. So you're working with very low-level structures. You're manipulating the machine because, and you want to do that because you're working directly with the outside world. You're interacting with sensors, you're interacting with electronics and communication protocols and stuff like that. And that language, C and C++, are designed specifically to do that. They're one of the older, some of the older programming languages, and they were designed to build directly off of the silicon that is running these things. Conversely, things that are higher level, like somebody mentioned doing finance. In finance, we're doing a lot of mathematical operations. We're doing a lot of high-level statistics and things like that. And you'll see things like the Python language being used with some extensions. There's a language called R that's specifically built around doing statistics. MATLAB and even Excel. Excel itself is a language that Phil was telling me about yesterday. I think you called it, was it reactive?
Yeah, it's a reactive style language.
Yeah. Yeah. So in general business, you'll see things like Java and C#, which are more object-oriented languages, and they're designed to help build large, complicated systems more easily. And then in the web, our interface, the environment that we're working in for this class, are built around languages like HTML5, PHP, JavaScript, and SQL, which is a database language that some people have already mentioned in the class.
And we can relate this question to the languages that we've chosen for this class as well, starting out with Python and transitioning to Java later in the class. Not only is Python, in our opinion, one of the better languages to start learning on, it's also, unlike languages like Scratch, which are good languages to learn on, but they tend to be more of a toy language, and that's all they're good for. Python is a powerful programming language that's widely used across the industry, and skills for Python programmers, or demand for Python programmers, is really high.
Yeah, somebody in the chats just mentioned data science, and Python is a huge language for that. There's lots of libraries built around machine learning and artificial intelligence, and dealing with large data sets and stuff like that. Python is sometimes referred to as a systems language because it ties into a lot of different areas, and it makes it easy to glue together a bunch of different systems and make them talk to each other. So for instance, there's a library called OpenCV that does computer vision. It's a open source computer vision library. And that is all written in C, but it has bindings that allow us to access it through Python, which makes it easy to connect to things like other web sources, all kinds of different applications, and all kinds of new ways of doing it. So there's lots of different specifics for different industries and things like that. And a little bit of research will show you what most people are using.
The next question was, can any one specific programming language handle all the necessary work? This is a really great question. Technically, yes. Most of the programming languages that we've just mentioned in the last few minutes have a characteristic that's called Turing completeness. And what that means on a fundamental level is they're all fundamentally equally capable. They're all equally capable of getting a computer to do anything that the computer is physically possible. It's physically possible for that computer to do. So it's possible that we could have one programming language that we all used and we could get everything done. But part of the reason that we have so many different programming languages, there is no one best language for all different types of applications. And in my opinion, there probably won't be for quite some time, if there ever will be. So for particular applications, particular types of things, for example, you were talking about finance and a lot of the mathematics that goes on there. Often we want to be able to manipulate large matrices of numbers quickly and efficiently in a language. And some languages like R and MATLAB have built-in features for that, whereas languages like Java don't. We would have to end up writing quite a few more lines of complex code in Java to do something that we could do in 1 or 2 lines in MATLAB. So while most of these languages are technically equally potent in their ultimate abilities, the actual ease with which you can get certain things done in one language versus another language is going to vary greatly depending on the task.
Mm-hmm. Totally. And it's really because a lot of these languages, they're built for their domains. So they've got a lot of features that have been built into the language that make them easier to use. Their common operations in a particular industry, those become part of the language. So rather than having something that's good at everything, you're just going to end up with either it being too abstract or not enough or too detailed for whatever application you're trying to solve. And it really depends. And that's why there's so many different languages. It's all specialization around trying to do a specific set of tasks.
Okay. The next question was, how do different cultural languages affect computer languages? That's another very interesting one. What are your thoughts on that?
I'm sorry, I was reading the chat.
Oh, that's all right. I'll take this then. So we were talking about this just yesterday, and very interested in this question. And one of the things that we discussed is the fact that most of the programming languages, especially the languages that we're familiar with, use English and English-like keywords in the language itself. And the reasons behind this are, some of them are fairly obvious. At least a third of the programming languages that exist were developed in countries where English is the primary language. But even programming languages like Python was developed in the Netherlands. Most of the keywords in Python are English-like as well. And I think that just kind of, there's a lot of historical reasons for that, but it's by no means universal. There are programming languages. There's one called Fjolnor, which is an Icelandic programming language, and there's another one called Jim, which is an Arabic programming language. And I haven't studied either of these, but I suspect that it would be very interesting to see how those languages, those programming languages, are structured differently based on the fact that the human languages in which they were conceived is also structured differently. But I'm not sure we can actually answer the question.
Yeah, we're that's a hole in our knowledge there, and we mentioned talking to a linguist before. And that's something that we would love to bring into the class. It was something we were trying to do before this class started. We have a lot of great ideas for how to make this class broadly applicable and bring in all kinds of different industries and stuff like that. But we weren't able to pull that together ourselves this time. But we'd love to explore this in the class a little bit more. Part of the idea around this too is that as you learn a language, any human language, it changes how you think. The way the grammar is structured and the way that sentences and communication is done in a human language changes how you think of different things and how you sort of reason in that language. And programming is exactly the same way. As you learn a programming language, as you learn different types of programming languages, it forces you to think in very different ways. And I know Phil was telling me about his Scheme experience and how that changed how he looks at how coding is built. He didn't really understand recursion, which is a topic we are going to talk about later on in the course, until he learned a totally different language that you can't do anything without recursion, right? So it kind of forces you into these different mindsets.
The next question was, can this algorithms and problem-solving approach that we're learning in this class be applied to other programming languages, or is it different from other languages? No, absolutely. The fundamental skills, problem-solving, and developing algorithms that we're learning in this class can be applied very broadly across probably all programming languages. There'll be some differences when you get down to the details of some very different types of languages, but for the most part, these skills are directly transferable to other languages that you'll learn. That being said, if you write the same program in two different programming languages, like maybe you write the program in Python and you also write the program in Java, they will look rather different, but be capable of doing precisely the same thing. The problem-solving process that you would follow to develop those two programs is going to be the same. The result's going to be the same. I guess an analogy might be, if you had to write a set of instructions for assembling a piece of IKEA furniture in English versus having to write the same set of instructions in Japanese. The process that you would go through to create that set of instructions is going to be pretty much the same. The result is going to look different, but to an English, someone who reads English, the English instructions are going to be just as effective for someone who reads Japanese. The Japanese instructions will be effective for them. Totally.
I want to hit some questions from the chat log, or from the chat real quick here. And a couple of them are related. We had a question about whether this is the first class in a series, and if we teach, or if any of the other classes in the series have been built. This is the very first class in programming. It's an introduction to programming class, and what we are going to be doing in this class is giving you some fundamentals of programming and preparing you for classes that may come later in the sequence. Where ASU is trying to build out the entire first year sequence for engineering and business, anything you need to take to basically experience a freshman year online, we're trying to provide. This is the first time they've developed a programming class, so we're trying out a lot of things new here, and that'll inform development down the line. We're currently not planning personally to build the next one in the class, but anything we do here will inform that. We'd love to, if that's an option. We had a lot of fun, are having a lot of fun with this class, so we hope to be able to continue that work later on in future classes. But there are lots of options out there if you want to pursue more stuff in this class. The next question that we had was about the level of detail we're expecting in the coding assignments. The one that I think we're talking right now about the pseudocode assignments and things like that. In this part, it's a little at the beginning here. We're looking for sufficient detail. It shouldn't be short, but it shouldn't be overly detailed. You kind of have to read your audience and who you're talking to and make some assumptions about what they know and provide the appropriate level of detail. And trying to figure out what that level of detail is part of the exercise. That's something that we want you to learn as we're going through this process.
So maybe a good rule of thumb or a way to test your algorithm. So say, for example, it's the sorting a deck of cards. You should be able to take a deck of cards and your instructions for sorting a deck of cards and hand them to someone, maybe a brother or sister or a mother or father or a grandparent, and ask them to follow those instructions and see if they end up with a sorted deck without you having to intervene and say, no, this is what it says, or this is what you need to do. If they have to ask for some additional feedback or they're confused by anything in your instructions, then that might indicate that you should add some detail or revise some elements of your instructions.
Yeah, that's a good rule of thumb and a good way to test and see if your thinking is following the idea that we're trying to do here. Okay, so back to our regular set of questions. Somebody asked if we're talking about how computers do calculations and that they have some fundamental limits to how they to memory and using the and stuff like that, right? You've all experienced it when you run a lot of programs on your computer starts to slow down, and that's because it's running out of memory, it's running out of resources like time and power and stuff like that. And somebody asked, as computer science, as programmers, how do we work around these limitations? And that gets really, really to the heart of what it is to be a computer scientist. Computer science is all about the study of how we can create algorithms that work efficiently to conserve memory, to be fast, and to solve the problem, right? We have a problem to solve. We need to solve that problem. What's the most efficient way that we can do that? And as you are new programmers, it's kind of hard to see this, but there's lots of algorithms, lots of ways of solving problems that have already been developed for this exact type of thing. And most of them have what's called a space and time trade-off. We talk about space as in memory, so either it uses a lot of memory and goes very fast, or it goes really slow and works in a tiny, tiny amount of memory. And usually that's the trade-off that we have when we're working with finite resources for something like this. Trying to balance those things or trying to match whatever the application is. In a lot of applications now, we are seeing this a lot. So for instance, when you're served a web page or something like that, a place like Facebook has a whole cluster of computers that is doing just what is called caching. So rather than spending time in going and searching for the page that you're looking for, it holds in memory the most frequently used pages on the most frequently used pages on Facebook, so that anybody that requests them gets it very quickly rather than having to go and find it and access it every single time, right? So that's what's called caching, and that balance of time and space, they dedicated a lot of extra space to make things fast. That's the heart of computer science as a whole. And as you gain experience, you'll see lots of ways of doing that exact type of trade-off for specific applications, and you'll be able to develop your own methods.
Right. There's a third side to that coin too, if to create a bad metaphor there. The space-time trade-off. There's also the source code complexity itself. When we write a solution to a problem in a programming language like Python or Java, often we're dealing with a complex problem and we're trying to express a solution to a complex problem, and we'd like to express that solution in as simple a way as possible. That way, if we have some sort of inaccuracy or some error in there, it's going to be much easier to track down that error. And so we're also sometimes or often trying to balance simplicity in the code that we're writing against those additional trade-offs of it should be fast enough and it should run in as little memory as possible. So it's a bit of a balancing act, and experience is the only way you're going to really acquire a sense for this. At this stage of the game, we are just wanting you to start developing solutions that work. You can lean pretty heavily on these machines nowadays. They tend to have a lot of memory, and the processors tend to be pretty quick. So I wouldn't worry about it too much at this point. But when you move on to subsequent courses where you'll focus on things like specific data structures for efficiently using memory and specific algorithms for efficiently using the CPU cycles, that's where you'll start to focus on those specific things.
Yeah, yeah. And one of the, I used to be of the camp that I would try to be clever and make things run super fast, everything run super fast and super low memory and stuff like that. My code was always a nightmare to read. And when I started working with Phil and one of our other colleagues, I learned the rule of make it work and optimize it later. If it just works, fantastic. 80% of the time, it doesn't need to be optimized. There's very small sections of any program that really affect performance a lot, and you're just hurting yourself by making it hard to read and hard to come back to and hard to maintain. You're building bugs in yourself. So if it just works, you've done the job, right? So, and that's all we want to focus on in this particular class.
So the next question was, for complete novice, how can this course guide you through coding for finance-related purposes?
Yeah, so in this case, we're going to answer this very generally, right? Because I think this question applies to a lot of people about they want to go into a specific industry and use these skills, right? What we're teaching in this class is a set of problem-solving skills, and really that's applicable almost anywhere. If you approach things in a systematic way and solve them in a systematic way, and you have some tools to create those solutions, you're going to be able to do lots of different kinds of jobs that are much better. So we're laying the foundation here in this class, and trying to give you the tools that allow you to grow in your careers as programmers in a lot of different ways. So we can't be really specific on a lot of these because it's different everywhere, different at different companies, it's different in different industries, and we're trying to give you a set of tools that are going to be useful almost anywhere you go.
Right. I think a good way to look at it at this stage is what the computer is good at, and what programming is good for is automating processes. So if it's something that you could probably do yourself, though it might take you far more time and effort than you have available to you, if we can construct an algorithm, design and construct an algorithm to get the computer to do it for you, it can probably do it millions of times faster and with significantly fewer mistakes. And so that kind of an advantage can be applied in finance and a whole host of other areas. And so those are the fundamental skills that we're focusing on in this class.
Mm-hmm. So we're going to end up here with a couple of other questions, and these are artificial intelligence related questions, which is a particular interest of Phil and I. I got my degree in computer engineering, but my focus when I was doing my PhD was computational intelligence, which is kind of like the grown-up, more, button-down shirt, working every day version of artificial intelligence. So I know a lot about this stuff, and we can help answer some questions. And the first one was, what's the difference between machine learning and artificial intelligence? And our perspective is that machine learning is a subset of artificial intelligence. Artificial intelligence is a really giant umbrella of different ways of solving problems. And really, any program that makes a decision is a kind of artificial intelligence. We're developing programs to stand in for something that somebody would be doing intelligently. They would be making decisions. Somebody intelligent would need to be there to make those decisions and take those actions. And we're developing programs that do that instead. So any program, in our very general definition, is a kind of artificial intelligence. What the field of artificial intelligence is related to is to elevating that level of problem solving. So we have some very simple but large systems that are called decision or expert systems that are just a chain of decisions, and how those decisions are made are based off of processing a whole lot of data. And the next question was, machine learning. Machine learning specifically is a way of developing a kind of program that rather than you setting all of the behavior of the program at the time that you wrote it, you set it up so that it learns from experience. So you expose it to data, it finds patterns in those data, and then tries to exploit those patterns to solve some kind of problem. So examples that we've seen are things like recognizing pictures of cats. That's Google's big project, and things like that. They took a program and they exposed it to lots of pictures of cats and lots of pictures of not cats, and it was able to learn the difference just by looking at the information that it was fed. And you could do the same thing using the same program. You could have it recognize, if you watch Silicon Valley, hot dogs. It's either a hot dog or it's not. You give it a bunch of pictures of hot dogs, you give it a bunch of pictures of not hot dogs, and that same program would classify one or the other in those categories.
So you want to talk about a little bit about where you think we are right now in the state of the art with these machine learning algorithms?
Yeah, so things are getting crazy. There's a lot of it's kind of a new renaissance for artificial intelligence. Machine learning in particular, now called deep learning, stuff like that. These are all a suite of methods that have been developed and recently deployed in common applications. So we're seeing them a lot more in real world applications where they used to only be in academia and kind of an abstract application. So now we're seeing a lot more of it, and that's really exciting. There's a lot of new developments happening, but we're nowhere near what they call an artificial general intelligence, which would be something human-like or something that we can interact with. Siri and Google, the talk interface, the voice interface, and Cortana and Alexa are an interesting new avenue. They're using artificial neural networks and different processes to process human speech, and then to match those to query patterns and all kinds of stuff like that. And that's really exciting. And all of this stuff is kind of, it's growing in complexity every year, and it's really exciting to watch. But I think we're pretty far from having a real, like, Terminator style thing running around.
Hopefully not Terminator.
Hopefully not Terminator. Hopefully something a little more benign in there. Yeah.
Do you want to talk specifically about neural networks?
Oh, yeah. So can you describe what a neural network is? So in our brains, we have these cells called neurons that help us make decisions and communicate information and all kinds of stuff like that. And we've known about neurons for many, many years. Back in the, was it 50s? Do you remember when McCulloch-Pitts was?
Yeah, it's about there.
Yeah, around the 50s. So around the beginning of the computing age, we were already trying to make our computers behave like human biology, or actually just biology in general. And one of the first models we had was called an artificial neuron. And a human neuron, actually any biological neuron, one side of the neuron collects information from a bunch of other cells. It does a little bit of processing, and it spits out an answer as a signal. It's in human neurons, it's a pulse of electricity. In artificial neural networks, they collect in a bunch of floating point numbers, do a little bit of processing on it, and then produce a floating point output. And this is a very general approximation. Biological neurons work in the time domain. So when two or more signals arrive in the neuron at the same time, they have to sync up and line up at the same time before the neuron will fire. And there's a little bit of processing that happens in there. So everything happens based on time, and we have loops, and we have all kinds of massive connections and massive complexity. There are billions of neurons in between your ears to make all of this experience happen. And we're nowhere near that level of complexity, even with the individual neuron itself. The artificial neural networks work on a similar but very approximated set of principles. And they don't work exactly the same way, but they're showing to be pretty powerful with the tools that we've developed over the years. Yeah.
I see a really cool question in here asking, why are we learning 2 languages in an introductory class instead of focusing on just one?
Awesome. So this is something we have fiercely debated with ourselves and other faculty here at ASU many times. And the reason why we have 2 languages is, one, we wanted to start with a language that is very approachable. There's not a lot of extra fluff. Phil was talking about the sort of extra syntax that can happen, particularly in a Java or a language like Java or something like that. In one line, we can do hello world in one line in Python. In Java, it takes at least 8, right? And so, because there's a lot of extra setup, and we didn't want to have to explain all that extra setup. We just wanted you guys to get in and programming and building stuff and making it work, right? So that's why we started with Python, but there's a lot of advantages to learning a language like Java later on. So we wanted to expand those capabilities, and the biggest thing is we wanted to teach the concepts of programming separate from the language, right? And to do that, the best way that we thought to do that was to teach 2 languages. So we're doing the same concepts of sequence, decisions, looping, and did I miss one? Classes and objects, stuff like
functions.
that. Functions, yeah, functions, stuff like that. We're doing those same concepts in both languages, and what we hope will happen is that you'll get a sense of what those concepts are separate from the language. So you'll be able to translate those concepts and have those concepts be reinforced across any language that you learn. And for us as experienced programmers, we can probably pick up a language, the heart of a language, in a weekend or a couple of days, something like that, just by doing a little project. We don't have to relearn all of the concepts over and over again. We just have to learn the syntax, because all the concepts are the same. We wanted you guys to have that first experience as well. We want to solidify those concepts by switching to a different language halfway through.
Right. Yeah, because from my own experience teaching computer science courses for 17 years, when you teach an introductory course in a single language to a group of learners who've never learned to program before, they tend to confuse the programming concepts with the language, and they can't really separate them after they take this class. And so then if you introduce a new language to them, they struggle to learn that second language because it's so different, and they can't relate what's going on in that language to how they understand programming, which is in a completely different language. So what we're hoping to do, as you were saying, with these 2 languages is help you separate out those concepts that are fundamental computer science concepts from the application of those specific concepts in a language like Python or Java. And then hopefully this will translate for you into a much easier experience for learning a second or third or fourth language, because you'll be able to focus on the concepts and not get hung up on, well, we always did it this way in Python, or we always did it this way in Java. So that's our hope.
Yeah. I hope we get lots of options for you guys after this. We just had a question about whether we're going to learn SQL or TSQL in this class. That's beyond us, definitely beyond me. I'm not, I don't usually deal with databases or web services or anything like that. So I've had no experience with SQL, and it's not going to be in this class because that's a higher level sort of language than the principles we're trying to get across here. Some of the concepts that we're going to be learning are going to be applicable to those languages. They're database languages, so they're structured slightly differently. Do you have much experience with any of those?
I don't have a lot of experience with them, but I've used the languages. Depending on how much experience you already have in that area, I would say, somewhere around halfway through this course or by the end of this course, I would recommend taking a look at a website called www.w3schools.com, which is a tutorial website for all things web-based, which includes SQL. And they have a really excellent tutorial on basic SQL, which is done in an applied way. So you get to practice SQL programming on their website. So, but it is one of the more different kinds of language than the ones that we're using. Python and Java are relatively similar compared to something like SQL.
Yeah, and there's a lot of weird languages out there. I won't say they're weird. There's a lot of languages that have different approaches to what they call the model of programming. We talked about Scheme earlier, which is it's a functional programming language. The prototypical functional programming language is a language called Lisp. that was developed back in the day. There's what they call declarative languages. So Python and Java are procedural programming languages. They're built around things happen in a sequence, and any single statement when that statement is executed, that's it, it's done until we ask it to do it again or something like that. There are declarative programming languages like Prolog, which are basically large mathematical systems. What you're defining instead of a sequence of instructions to be executed is a set of mathematical statements, and how they interact is when the program is executed gives you the result overall. It's a very different way of thinking. And there's a lot of different models for programming out there.
Yep.
So last call for questions. We're a bit of a lag. I'm watching myself in the video over here gesturing away, and we should be wrapping up soon. So if there are no more questions, you can always post more. We're going to be doing this. Oh, we just got one. Looking at majors, I want to get into the field of computer vision. Would I benefit from computer engineering versus computer science? Ooh, that's a very good question. That was some of the reason why I got into computer engineering. I wanted to build robots when I first started out, and my university, which was Missouri Science and Technology, didn't offer a robotics degree. They had electrical engineering, mechanical engineering, aerospace, and computer science. And they had this new one at the time that was computer engineering, which straddled the line between electrical engineering and computer science. And I thought that was interesting because it was more of an interdisciplinary thing. What I ended up learning as a computer engineer was a lot more low-level hardware stuff. So it was where electrical engineering, the physical world, meets the computational world of computer science. If I were to do it again, knowing that I was more interested in artificial intelligence, I would go through computer science. I would get more of an education in algorithms. I would do more of the AI machine learning classes, and that would greatly inform my computer vision and stuff like that. I did end up working in those fields. I worked for Boeing doing artificial intelligence work. I worked on I was on the robotics competition team, and we did lots of computer vision stuff. I still love that stuff. It's super fun to do, and it's really crazy powerful. But to get to the heart of it, I would definitely pursue CS instead. Yeah, there's advantages for both of them. Okay, I think that's it. Oh, why so much? Jesus, you're killing us. No, it's awesome. I love your questions. Jesus, why so much math for CS? So the answer is kind of historical, but it's also fairly useful. So computer science started out as a mathematics discipline, right? Back in the day, the computer science discipline, computer computation, was a mathematical endeavor. So they all most of them started in the math department, and there's still a lot there. The pure computer scientists are people that will work in a mathematical domain to make proofs about algorithms and things like that. Those are kind of the highest level of wizard of computer scientists, and some of them don't even do coding. They just develop algorithms and do algorithmic analysis and proofs of different things like completeness and P equals NP and all kinds of crazy stuff like that. And that's a mathematical endeavor. There is lots of useful stuff in the mathematics domain that can be translated into applications of computer science, right? So if there are a couple of things that I found particularly useful in mathematics that applied to all the work that I did in computer science. One was numerical methods, and this requires some calculus and stuff like that. And what this environment is a way of solving problems that is computational in nature. We can use computers to solve these problems, but we wouldn't be able to find a numerical answer in any amount of time that's reasonable in any other way. So it's a way of approximating some of the answers to these real problems that are super challenging. And these problems show up in things like video games. They show up in real applications of dealing with systems that change over time and all kinds of stuff. It's a really common thing, and to be able to understand how these solutions work, you need a pretty strong mathematical background.
Right. Yeah, and you're talking about the theoretical side and the pure theoretical side of computer science there. I lean more heavily towards the applied side. And on the applied side, as you were just mentioning, the mathematics can come in very handy, but it's not just mathematics. And I want to dispel a myth just in case it's getting formed out there. You don't have to be some sort of excellent mathematician to be any good at computer science or writing programs for computers. Any additional skills that you have, if you're good at mathematics, or if you're just good at writing, or even if you're good at art or music, all of those skills have areas where you can apply them in algorithmic and computer problem solving as well. In fact, in my opinion, most of the interesting work that gets done out there in applied computer science is generally where computer science is combined with something like art or architecture or some other field that's not necessarily considered a part of computer science. But applying computer science to these other fields requires a knowledge of these other fields. So I really feel like there's literally, as a computer scientist or software engineer, there's nothing you can learn that won't in some way someday benefit you in your algorithmic problem solving.
Absolutely. Totally. Yeah. And mathematics is being fluent in mathematics or enjoying it is definitely not a requirement of being a programmer. So I avoid it as much as I possibly can. I've been talking a lot about it, how it's useful, but I flunked calculus the first time that I took it. I had to wait for a really good teacher to pass it, and I ended up not really liking it until I got to physics, where I could apply it, right? And it's about for me, mathematics supports the application. It's not just for the sake of it, and that's where it's really interesting. But you absolutely don't need it. There's a lot of tools out there to help you be good and do really complicated things without needing all of this calculus and stuff like that. I still recommend doing it because it's a healthy exercise. It'll make you a better thinker. It's going to be hard and it's going to be tough, but again, common message in this class is challenge is growth. So the more you challenge yourself, the more you're going to learn and attack those weaknesses rather than try to avoid them. And you'll be a better person. You'll be more powerful as a person on the other end.
I agree.
Awesome. So I think that's the end of our time here. I want to thank all of you guys for your participation in the chat room and on discussion boards. You guys are doing a fantastic job of helping us build a learning community. We really appreciate you talking to each other and supporting each other. Please continue. We'll be doing another one of these probably in 2 weeks. Then we can talk again about more things that you guys would like to do. Thanks, everybody.